So we're going to try and solve this recursively. And I'm putting this in quotes because we're going to express this recursively, but we'll see that it's actually easier to build up, more convenient for us to build this up from the bottom up rather than from the top down. So the idea here is that we're going to define our solution in terms of subproblems. So if we have a chain of matrices, this is maybe not the full chain, but we're starting at some matrix A sub I, and we're multiplying all of the matrices all the way up until A sub j, how would we get the least number of scalar operations in order to multiply all these together? Well, let's say we had already a solution to this. So the least number of scalar operations in order to solve this, multiply all these matrices together, is nij. So this is just a table which represents if we start at A sub I and we go all the way up until A sub j and we're taking the product of all of those elements, n at this value will give us the least number of operations that it takes, the least number of scalar operations that it takes in order to multiply all those matrices together. And the idea here is that we can define an optimal solution for our entire problem, which would be the least number of scalar operations that it takes starting at A sub 0, our first matrix, and going all the way up until A sub n minus 1, our last matrix, using solutions, optimal solutions to these subproblems. So that means that our subproblem exhibits what's called the subproblem optimality property. So that means that there is an optimal solution, which we can define in terms of optimal solutions to our subproblems. And why this is the case, if we look at all possible, this entire chain of matrices we multiply together, A0, A1, and so forth, all the way up until A n minus 1, in our solution, at somewhere in this, we'll have the last multiplication that we perform. This is the root of our expression tree. So let's say the last multiplication that's incurred happens right after index I. So that means this is our last multiplication here. Well, if this is where our last multiplication is, then we can express the least number of scalar operations it takes to multiply all of these together, starting from 0 and going up until n minus 1. We can express this as two things. One, how we build, or three things. One is how we build this left part of our matrix, left chain, and then how we build this right chain, how much it costs to build that right chain, and then how much it costs to multiply now these two matrices together. So the cost of multiplying all of these matrices together from A0 up until AI is exactly our subproblem, minimum number of scalar operations it takes to multiply matrix A sub 0 all the way up until A sub I, plus however much it costs to form this right matrix. So we have to multiply matrices from A sub I plus 1 and go all the way up until n minus 1. So this is the minimum number of scalar operations it takes to multiply this chain together, plus now that we have this left matrix and this right matrix, how much it costs to multiply those two matrices together. And this is based on the product of their dimensions. Now, based on what the dimensions of each of our matrices are, this will be a D0 matrix by Di plus 1 matrix. And this one will be a Di plus 1 by Dn matrix. So the product of our dimensions are just D0, Di plus 1, and Dn. Now, the optimal solution for our entire problem is based on the optimal solution for subproblems. Otherwise, if we could solve this in a better way, one of these, either the left or the right matrix, then we would come up with an even better solution using that solution for our subproblem, which uses less scalar operations. Which means that our optimal solution is written with respect to an optimal solution to our subproblems. Okay, so we're going to use that characterizing equation in order to help us figure out the total number of scalar operations that we can solve this chain of matrix products using the least number of scalar operations. So this is that one which I wrote previously. So the idea here again is that since we're going to put this in a table already, I'm going to write it this way. That the minimum number of scalar operations it takes in order to start, so this is our starting point, starting with a sub I and going all the way up until and including multiplying all the way up until matrix A sub j. So we're always going to have I is less than or equal to j. So starting with a sub I going all the way up until a sub j, how many scalar operations are required minimally? What can we do this in? So this is the cost of forming our left matrix, forming our right matrix, and then multiplying those two matrices together. So if we have here a sub I all the way up until a sub j, somewhere we'll have that final multiplication. Maybe we split this at a sub k. Okay, it could be anything. Which means when we multiply this entire chain together, first we figure out what the product of this smaller chain is, and then we figure out the product of this smaller chain, and then now that we have one matrix on the left, one matrix on the right, we multiply these two matrices together. So this is the idea here, where our split, our last multiplication, occurs immediately after index k. So somewhere this happens, somewhere we have this last multiplication. But the number of scalar operations which we'll use is equal to however much it costs for us to build up this left chain. So here we're starting at I and going all the way up until k. So this is the minimum number of scalar operations that it takes to multiply starting with a sub I and going up until a sub k, plus however much it costs for us to build the right matrix, which is starting at a sub k plus 1 and going up until j, plus now that we have these, let's call it matrix L and R, we have to multiply them together, and the cost of multiplying these two matrices together is based on the product of their dimensions. Now this left matrix is a di by dk plus 1 matrix, and our right matrix is a dk plus 1 by dj plus 1 matrix. Okay, so we can figure out the total minimum number of scalar operations required if we can solve for this value. But the subproblems that we have are not independent, and this is also why, even though it looks like we are breaking up our problem into subproblems, we also can't use a divide and conquer approach here exactly because the subproblems that we have are overlapping, they're not disjoint. Because when we end up solving for, let's say, we have this chain of matrices going up until, let's just say, A6. In order to figure out the best way to multiply a sub 1 all the way up until a sub 6, we have to figure out the best way to multiply a2 up until a4. And we're also going to use that solution in order to figure out not just how we multiply all these matrices together, but also how we would multiply a sub 1 to a sub 5 together, or a sub 2 to a sub 5, or a sub 1 to a sub 4. So there's an overlap of subproblems that we end up using here, which is why we don't want to solve this exactly recursively. Instead, we're going to define this from the bottom up. So the idea is, since we end up reusing these smaller sized subproblems, we're going to solve for these smaller sized subproblems first, and then use them in order to give us a solution for our larger sized problems. So the idea is we're going to figure out the best way in which we can multiply a chain of matrices together of a small length, and then use that to figure out how to build up, how to multiply a chain of matrices together of a larger length. Okay, so we have, here's our end table. I represents our start here. So this is our starting matrix. So we're multiplying at a sub I, and we're ending at a sub j. So we have across each diagonal all of the matrix chains of length 0, because in this case, if we start and end at the same point, so from a sub 0 up until a sub 0, we just have the matrix a sub 0. We actually don't have to do anything in that case because we're not multiplying any matrices together. Or if we start at a sub I and we end at a sub I, again, we're not doing anything. This is just a chain that consists of only one matrix. And we're going to use these values in order to help us figure out what's the best way to multiply now a chain of two matrices together. So this would be, here we start at a sub 0 and we go all the way up until a sub 1. Or here we start at a sub I and we go all the way up until a sub I plus 1, the next matrix. So each diagonal corresponds to all of the chains of matrices of increasing length. So we've got everything of length where we just have one matrix, where we have two matrices, where we've got three matrices and four matrices and five and so forth, until we reach this last cell, which is exactly what we want to find. This is if we're starting at a sub 0 and we multiply all the way up until a sub n minus 1, which is the last matrix we have. So this is what we want to compute. But in order to compute this, because we're going to reuse the problems that the smaller size problems, we're going to figure out a solution for these smaller size problems first, and then work our way up to this longer chain of matrices. Now, in order to solve for this, again, we're going to use the solutions we had for our smaller sized problems, subproblems. So for example, if we want to figure out what's the least number of scalar operations it takes to start at a sub I and go all the way up until a sub j, what is the minimum number of scalar operations it takes to multiply those matrices together. This is based on where we do our last split. So either here we're going a sub I, let's put a plus 1, I plus 2, and here's our a sub j. So in this case, we've got 1, 2, 3 places where we could split. Either we do our last multiplication here, right after a sub I, or we do it here, or we do it here, right after I plus 2. So those are the options that we have. And this corresponds to the previous cells that we've got here. If we split at a sub I, then we've got, this is the cost to form the left matrix, plus this is the cost to form the right matrix, plus we still have to add the product of the dimensions. Or if we split here instead, we've got, here's the cost to form the left matrix, plus the cost to form the right matrix, plus the product of their dimensions. Or in the last case, if we split right after I plus 2, then here's the cost to form the left matrix. This is starting at I and going all the way up until I plus 2. Here's the cost to form the right matrix, plus the product of their dimensions. So you're going to see an example of this in the next video. So check that and make sure you really understand how this characterizing equation works. But the total runtime of this is big O of n cubed. And this is because we've got n squared cells here, and in order to fill a cell, we may have to go through the n previous cells coming before it. Now we can record along the way what was the best place where we performed that last multiplication, so that we can use that to build up when we're finished with this. This will give us the minimum number of scalar operations, but in order to figure out the full parenthesization, we have to figure out where we performed those last multiplications, which gave us that minimum number. So we can do that by remembering separately a k table as well, of what was that minimum number k of all of these possible values where we could do our last multiplication, which one of them actually gave us the least number of scalar operations. Okay, let me show the algorithm for this first, and then we'll do an example. So we have a sequence of n matrices. We want to multiply them all together. Before we multiply them all together, we want to figure out the best parenthesization for them, which is based on the dimensions of those matrices. So we have for matrix, let's say A sub I, the dimensions of that matrix is D sub I by D sub I plus 1. Now what we're going to do is fill in the first diagonal. This is for every place, every cell where we have the same starting point and the same ending point. This is that we have just one matrix that we're working with, that A sub I, in which case we don't have to multiply anything together, so that doesn't cost us anything, so we can already fill in those values. And then we're going to work in increasing length chains, beginning with a chain that has only 2 matrices, and then all chains of 3 matrices, all chains of 4 matrices, and so forth. Now for them, we're going to figure out, okay, this is our length, this represents our increasing size chains, how many matrices are in this chain. We have some starting point, I. So for every possible starting point that we have, we can figure out what the ending point would be, because this is based on how many matrices are in this, how many additional matrices are in this chain. And then we're going to compute the value nij. So this is the minimum number of scalar operations it takes to multiply the matrices A sub I, multiply this all the way up until A sub j. So I gives our starting point, j gives our ending point. We're multiplying all matrices up to them. And we're going to figure out what the minimum value is. So initially we're going to start this off as positive infinity, or just integer max, and then find where among all of the possible places that we could perform our last multiplication. To illustrate that, maybe we perform our last multiplication here or here. This is just a way in which we could parenthesize them, and we're indicating where we're parenthesizing them using this index k. So k gives us A sub k, let's draw that here. This indicates where the last matrix in our first parenthesization is. So our multiplication occurs immediately after A sub k. So k is indicating where our last multiplication is. And we're not sure where it should be, so we're going to try all possible options of where we could do this last multiplication, from I all the way up until right before j, and compute between all of those different options the better of whatever we had before, if we had already recorded even less scalar operations using some other k value, or if we find something better, this would be however much it costs to form the left matrix, multiplying A sub I all the way up until A sub k, however much it costs to form our right matrix, going from a k plus 1 up until a j, plus the product of the dimensions of those left and right matrices. So the dimensions of our left matrix here is di by dk plus 1, and the dimensions of our right matrix is dk plus 1 by dj plus 1. And when we do this, if we end up finding that, oh, this k value actually gives us a better value, meaning this one is smaller than whatever we had recorded before, then we're going to record what that k value is. That way later we can reproduce it.